Nanoparticles are frequently used for drug delivery. They can control the release of a drug over time or help target drugs to specific cells. Today, we're making polymer nanoparticles that use long chains of molecules called polymers that contain both hydrophilic groups, which like to interact with water, and hydrophobic groups, which avoid water. We'll use a technique called self-assembly, where the polymer chains spontaneously organize themselves into nanoparticles when the solvent changes. So here's how it works. First, I dissolve my polymer in a good solvent, which means the entire polymer dissolves well. Usually for nanoprecipitation, this means picking an organic solvent like tetrahydrofuran. This is also the stage if I would add a drug molecule, but today we're adding a dye instead, so it's easier to see. Next, I slowly drop my polymer solution into an anti-solvent, in this case, water. You'll notice that I have a stir bar making a vortex in the water. This is so the polymers rapidly get dispersed in the water and result in many small nanoparticles versus a few large aggregates. When we drop the polymer solution into water, the more hydrophobic parts of the polymer are plunged into a bad solvent and want to hide from the water. The hydrophobic sections of many polymers gather together, while the hydrophilic sections remain on the outside, forming stable nanoparticles with hydrophobic cores and hydrophilic shells. These nanoparticles form almost instantly as the polymer meets the water. After I finish adding all the polymer, I'll leave this solution stirring overnight, so the remaining tetrahydrofuran can evaporate, leaving a stable suspension of nanoparticles. And that's how you make nanoparticles. From here, we can take our nanoparticle solution and test for their size, or look at the rate of drug or dye release from the particles.